First of all, I would like to express my thanks to the conference organizers. It was very gracious of them to invite me and kind of them to have invited me. I'm not going to, I hope I will be able to touch upon engineering 2D materials. I have not yet started on engineering these 2D materials, but we have results on some 2D systems that we have started working on. I primarily come from a background of studying topological insulators and superconductors. And recently, I do a technique called magneto-optical imaging, some of which, very little of it I'll try and show towards the end of the talk, because of which we can look at local magnetic fields inside materials, and because of which some of my collaborators sent me some crystals of 2D materials. So these are the crystals from IISc Kolkata, CGT, chromium germanium telluride, and FGT from Ravi Prakash and Rajiv Mandal. I'll basically concentrate on my studies on chromium germanium telluride CGT system and tell you some of our recent results on them. The work is essentially of those of my students, Pranesh Mahato and Shupratim Shaha. They have been the one who did the work, and Saurav Mal did the DFT calculations, which we did along with Prasenjit Sen at HRI Allahabad. So let me tell you something about the system that we have studied, and these are the funding agencies. Basically, I'll give you a brief introduction. It's not required for this audience, but magnetism at low dimensions is, if you have a 2D Ising model, then you can see the exchange interactions allows for a nice a phase transition to be seen inside the system. There is symmetry breaking, and you will see divergence of susceptibility, correlation, lengths, and so on. If you go to the 2D XY model, then of course fluctuations start dominating and you will lose the phase transition, but you still see a BKT-like transition because of a binding and unbinding of defect pairs. But when you go to the Heisenberg system in the 3D case, then the fluctuations sort of kill all order inside the system, and you don't see in this 2D, in the 2D case, when you have this three-dimensional Heisenberg spin, you don't see any order emerging inside the system. And so if you have exchange interactions, then of course, as you go across your ordering transition, there are these long wavelength Goldstone modes which are generated. These are the magnons which are generated, and they are typically gapless. And so you have these magnons which can spread out of the system, and you lose order inside the system. But you can still allow order to emerge inside these 2D systems by introducing anisotropy inside the system. The anisotropy may emerge from spin-orbit coupling. There can be a shape anisotropy because these are highly shape anisotropic systems. It's two-dimensional, so there is no thickness on the z direction, and it is so there is a lot of anisotropy that is there in the system. And because of the presence of this anisotropy, often the magnonic spectrum is gapped out, and you really need, there is a certain energy cost to excite the magnons, and therefore you can actually stabilize an order inside, even in 2D systems, magnetic systems. And that's basically that anisotropy is very important in these 2D systems in which magnetic order can emerge, and we can study some of these magnetic order in these 2D systems. So basically, for engineering some of these devices, you really have to cleave out and make these systems very, you have to cleave them and bring them to the 2D limit. So basically, we were interested in these 2D van der Waals materials. And one of the system that we are looking at, or I will present to you, is this chromium germanium telluride system. So the system is basically, it has these chromium atoms which are surrounded by an octahedra of tellurium atoms, and they are arranged in this form and in this sort of a honeycomb-like structure, in between which you have the germanium atoms which are sitting, which are shown in green. The chromium atoms are shown in blue, and the tellurium atom octahedra around the chromium atoms are shown here in orange. And this layer, this sort of a structure is arranged in the ABC stacking, and you have this sort of, this layer is separated from another layer with a van der Waals gap. And these are very weakly coupled van der Waals materials. The gap is around 6.81 angstroms, and you can cleave them very easily. So they are very easily cleavable, and they talk to each other very little along the z direction. So these materials have were first sort of, I mean, they were found and they were studied in 1995, and there were a lot of mysteries which were still found at that point of time. What you find is that there is an ordering temperature in this system. The CGT system has an ordering temperature around 67 Kelvin, and there is a magnetic moment of chromium which develops around 3 μb in the material. And you can have, you can see this ordering occurs in the system because you can see a bump in specific heat. And this system, actually the transport in the system shows that it is a semiconducting system. It has an indirect band gap of around 0.4 to 0.7 and a direct band gap of around 1.2 eV. So these systems are ferromagnetic semiconductor van der Waals material, which can be very useful for making various sort of spintronic devices. So this was the primary motivation that we got interested into looking at these 2D materials. And the thing is that if you want to make these devices, you need to cleave them out and bring them to 2D, down to 2 dimensions. So how is the magnetism retained as you lower the dimensionality of the system? As you make it thinner, what happens to the system? So there have been a number of recent studies where people have been interested in this system. And this is a small piece of the CGT material where on one end it has about 4 layers, and then the other, as you walk along this, it has 3 layers, and towards the corner you have 2 layers. And this is the Kerr signal that is measured at different points. Wherever it is thick, you can see a good ferromagnetic transition. But as you walk along this, this is at around 40 Kelvin, you can see that there is a proper ferromagnetic signal, Kerr signal, which is coming from this thicker layer. But if you have to see the transition, it gets weaker as you go to the thinner layers. And you also see that there is a shift in the transition temperature. So it is found that the magnetism does get slightly weaker as you go to thinner layers, and there is also a slight shift in the transition temperature which is seen, the ferromagnetic transition temperature, as you lower the thickness of the sample. Now this chromium germanium telluride has an anisotropy which is perpendicular to the c-axis, and that's the easy axis, which has a lower saturation field, and along the AB plane is the harder axis. So if you take a crystal, this is the c-axis and this is the AB plane, you can see a difference in the MH loops which you measure along the c-axis and the AB plane axis. And this anisotropy, you can measure the difference in this anisotropy field, which is the saturation field, which is measured along the c-axis and along the AB direction. And there is a class of these materials, and if you plot the anisotropy field or the anisotropy energy, which is 3 μb times Hs for chromium, if you take the chromium class of materials and you plot it against the ligand spin orbit coupling strength, then you find that for these class of materials, as the spin orbit coupling strength increases, the anisotropy strength also increases. But chromium germanium telluride is not following that feature, although it has a sufficiently high spin orbit coupling strength, its anisotropy is on the lower side. So there are there are some interesting features which appear in this chromium germanium telluride, and we definitely wanted to study what is happening in this system. Now, when we are going to make these 2D materials, we really want to thin them down to few layers, essentially go down to monolayers, and then we want to ask, does the physics remain the same as you thin down the material? And how do you quantitatively evaluate if your physics is going to actually remain the same as you thin down the material? Because magnetism could actually change and there could be thermal fluctuations, so there could be complex low magnetic dimensional dependent phenomena which can arise at lower dimensions. So what could happen and how do we quantify it? So one of the ways to quantify it is that there is of course a critical transition temperature inside the system, the ordering temperature, which is there inside the system, and you can the specific heat versus the reduced transition temperatures. This is well-known critical phenomena. They will have critical exponents associated with it. So as we thin down the sample, as we go from the bulk to thinner samples, what happens to this to the critical exponents? Because these critical exponents can actually be mapped to universality classes. There could be the Ising class, you could have the 3D Heisenberg or tricritical model mean field pictures. So there are various universality classes which can explain what is the nature of the critical exponents that you get inside the system. So our attempt was to measure before we actually make a very thin device and study it, we wanted to see does it remain the same when you go from the bulk to the thin 2D layer. And our basic philosophy would be to measure these critical exponents as we thin it down. So the basic question that we started off with is that you have a critical transition temperature in the bulk 2D system, and what is the universality class for this bulk CGT material? That's the first thing. Is it Ising-like? Is it XY, 2D XY? Is it Heisenberg, 3D Heisenberg? What is the nature of the universality class? And then as we thin it down to few layers, what happens to the TC of the material? As we lower them, as we lower the thickness, is the universality class preserved? Because that's very important, that whatever is the magnetic state, it is preserved. And these are the type of questions that we would like to ask. What happens to the magnetic anisotropy? What happens to the magnetic configuration? Those are the type of questions that we really wanted to ask as we thin down the crystal. So first, let me show you some of our results in the bulk CGT. So this is one of the samples, which is about 2.5 by 2.3 millimeters and about 20 microns thick. It is a single crystal, and you can see the single crystal peaks. The stoichiometry is uniform, measured across the sample. It's very uniform for chromium, germanium, and tellurium, maintaining the stoichiometric ratio. So this was one of the types of crystals, and we had quite a few crystals, and we measured them. And the basic measurement is, for the moment I'll show you, is magnetization measurements. So you have the magnetization versus field, which is measured, for example, here at 4 Kelvin, for H parallel to the C-axis and H perpendicular to the C-axis of the crystal. So in the two orientations, we can clearly see that there is a square shape of the hysteresis loop with a low saturation field for the parallel to the C-axis and perpendicular to the C-axis, or H parallel to AB orientation. It's the hard axis. So the single crystal is maintaining what we had known before, is that there is a C-axis oriented anisotropy in this single crystal. You can measure the magnetization as a function of temperature. This is the inverse susceptibility as a function of temperature. It shows a nice Curie-Weiss behavior, and it gives you a transition temperature of around 64 Kelvin and an effective moment of 3.18 μV per chromium atoms. Chromium is in the 3+ state. This is what is expected, and it is doing all of it which we know. Now, what you can do is that you can start doing the critical scaling analysis and try to determine around this temperature. You measure the MH hysteresis loops above and below this temperature. And so you measure M versus H across temperatures which are across the critical transition temperature. And then what you can do is that this MH, you can plot it in a certain particular way, where M raised to 1 by beta and H by M, the inverse susceptibility raised to 1 by gamma. The same thing, you can plot it. This has been measured across the transition temperature at temperatures above the transition temperature and temperatures below the transition temperature. And this same data is plotted in this way. And what you can see is that across a certain, if you find the beta and gamma value, you have to do it iteratively. You have to run a program to actually do this. But once you get the right values of beta and gamma, what you will immediately see that across a line passing through 0, which is this line is really the 67 Kelvin line. Anything which is lower than this, the MH has intercepts on the y-axis, which is your saturation magnetization, the extrapolated saturation magnetization, and anything which is on the x-axis is your inverse susceptibility above the transition temperature. So you can pick out these intercepts on the x-axis for temperatures which are above the transition temperature and the saturation magnetizations which are below the transition temperature. And what you will get is something like this. These intercepts plotted as a function of temperature shows that the saturation magnetization goes as the reduced temperature raised to beta. This is as per the critical exponents, and the beta, if you fit it, it is 0.12. And above the transition temperature, the intercepts on the x-axis, this is the paramagnetic susceptibility, the fluctuations, the critical fluctuations in the inverse susceptibility goes as T raised to gamma, and the gamma is 1.21. So you can very accurately figure out through this, and both of them are actually tending towards the critical transition temperature, which is estimated to be around 63.68 Kelvin. So this actually tells us what are the critical parameters for the bulk CGT, the 30 micron thick CGT. And we also measured the actual susceptibility as a function of temperature experimentally. And of course, this also shows the same gamma, which is seen here. This is about 1.21, we got it 1.31, but within the error bars, we found it was to be the same. And there is another parameter, delta, which is related to these beta and gamma parameters, which you can figure out using this relation. So you have the MH data, and once you figure out alpha, beta, and gamma, beta, gamma critical exponents, then there is an equation of the state, and it's a very nice exercise, because once you find the beta and gamma, the same data, you can, and you find out, okay, so the delta is, you can also find it magnetization as a function of field, and if you fit it, it's related to this exponent delta. That also turns out to be the same, which is evaluated from gamma and beta. But then the idea is that once you get this equation of state and you plot it m by t raised to beta and h raised to t by beta plus gamma, then the same MH curve actually scales onto two separate curves across the critical transition temperature. The whole thing scales onto two uniformly scaled curves, and the beta and gamma are very accurately determined. The critical exponents are determined in this way, and this is really the essence of the critical scaling analysis, is to break across a critical transition temperature, to break this data into these two scaled curves following the equation of state. And of course, this is just to show you that we tried different things, and only for a certain 2D Ising model, we could find that this sort of a scaling feature works. These parameters, beta and gamma, that we determined are really for the 2D Ising model. So the critical phenomena associated with the magnetic transition in bulk CGT shows that the spins actually follow the critical 2D Ising model. And so you have these 2D Ising like spins on the chromium atoms, which are sitting in this system. Okay, and this of course has been seen in the past also. People have reported this, that the bulk should follow the Ising like scaling. Is it uniform across other 2D systems, this sort of a critical scaling analysis? Just an aside, that we looked at CGT and we showed it was 2D Ising like. If you take bulk FGT, another sort of a very cleavable magnetic system, ferromagnetic system, which is very cleavable, you can do the same analysis across a transition temperature in this system, which is very close to room temperature, and that is why this is also very important for room temperature applications and devices. And if you actually we did the critical scaling analysis, again, the scaled curves are seen beautifully appear in the system, but the critical scaling parameters actually are for 3D Heisenberg. So it's not uniform across the spectrum of these van der Waals magnetic systems. They might be 2D Ising-like, or they could be 3D Heisenberg systems. This is what we observe in these systems. So as far as the bulk picture is concerned, at least in CGT systems, I'm going to go back to CGT and focus now on CGT, is we saw that it follows the 2D Ising-like behavior, and now we are going to actually thin them down and see what happens to the system. Now, earlier there have been a few nature papers on this, that people have tried to thin it down, and they could only go down to 19 nanometers of thickness of this. After that, they lost the magnetization signal. It was not measurable, and they couldn't do any sort of analysis of this sort. They couldn't follow up the analysis, but at least down to 19 nanometers, they found it was 2D Ising-like. It followed that feature. Now, what we did was, instead of using a silicon dioxide SiO2 substrate for these, for actually thinning down and putting the 2D layers on top of these systems, there is a lot of background which we were finding. There is a lot of substrate interaction which happens between the 2D layers of CGT and the substrate if you use SiO2. So instead of that, what we thought, which people had not, I don't know why they didn't do it, but in the 2D community, this is very regularly done, is we put them on HBN. And I will show you results of the Scotch tape cleaved 2D CGT, which we put on HBN. So this is the TEMs of these CGT layers which we have put on HBN, and we can see beautiful patterns. We can actually identify simulated the location of these patterns for chromium, germanium, and tellurium, very ordered structures. We looked at the Raman signatures for the 2D few bilayer and flake and the bulk crystals, and the Raman signatures are identified. They sit at the same location. This is the diffraction pattern, the selected area diffraction pattern. Again, these can be indexed and showed very well ordered structures. And what we did was that to measure this magnetization of these 2D systems, we put these flakes and we put multiple of these flakes on this HBN layer. Instead of one single flake, we had a number of these flakes so that we can get a sufficient magnetization signal when we measure it. And the color scale here represents the thickness of these. This is an AFM image which measures the thickness of these flakes, and we got very uniform flakes distributed across the HBN layer. So all of them have a height of around 2 to 3, the height variation of these flakes varies from 2 to 3 angstroms, and that is typically associated with at least 2 bilayers of CGT. So we have a uniform distribution of bilayers of CGT that we have generated on HBN, and this is the distribution, and then what we do is that we measure once you have this HBN substrate with 2 bilayers of CGT deposited on, placed on top of HBN, multiple such layers which are on HBN, we measure the magnetization versus temperature. You get a good signal. It's at the limit of sensitivity, but we are able to measure the magnetization. As you see that there is a transition at 67 Kelvin, which you see in the bulk, so that transition is maintained. Whereas in the bulk, there was an ordering transition at 67 Kelvin, and then the signal remains steady. What we find in the 2D layers of CGT is that below the ordering temperature, Below 67 Kelvin, it goes up, the signal goes up, but then there is another downturn. There is at 20 Kelvin, there seems to be something else which is happening in this system. So this is where we will discuss what happens in this 2D layers of CGT. So first is the transition at 67 Kelvin. Again, in this 2D layer, you can do the scaling, whatever I showed you, you can do a nice scaling of this transition at 67 Kelvin, and that follows that scales into the two scaled curves, and the parameters are close to the 2D Ising-like system. But yeah. No, this is CVD HBN. These are SiO2 on HBN on SiO2 layer. We have it has a variance between 2 nanometers to around 4 nanometers. So they are not all bilayers. These are exfoliated. Yes, yes. And there are multiples. We do multiple so that there are a number of flakes on this CGT, and we look at the thickness of all of them. And then after that, we have characterized what is the variance. We go and put it in the magnetometer and then measure the magnetization. Okay, so this is the magnetization. Of course, the magnetization signal is weak, but you can see the magnetization behavior as a function of temperature. And so this transition follows the uniform behavior. Now what we will look at is what is happening across this 20 Kelvin. And so we start from 2 Kelvin up to 20 Kelvin and go higher up. And we look at the magnetization as a function of field, similar to what I showed you in the bulk. We follow the same procedure. And the idea is that, okay, if you fit the magnetization, you get a magnetic moment again of 3 mu b, which is, so the magnetic moment is still remaining the same. And if you do the scaling analysis, which I showed you earlier, this data can also be scaled, and you can get, for this 2D layers of CGT, you can get as you go across the transition, you can get intercepts on the X and Y axis, you can plot them out, and you can see similar sort of behavior. And there is a critical transition which is sitting at around 12 Kelvin, and the critical parameters are beta equal to 0.21 and gamma equal to 0.8. If you fit these to the critical exponents, you will get the exponent values, and the exponent values around this transition now have completely changed. They have deviated from the 2D Ising-like behavior. They are no longer 2D Ising-like. You can again get the equation of state. The data is noisy, but it still breaks up into two scaled curves using these values of beta and gamma, and the TC is around 15 Kelvin. This is the around which there is this turnaround, the low temperature turnaround in the system. So what we find is that in the bulk crystal, whereas it follows a 2D Ising-like behavior, as you lower the thickness, there is a transition at 67 Kelvin, but there is also another transition which is appearing at lower temperatures at around 14 Kelvin, and the critical scaling around that is very different. It does not follow the 2D Ising-like. In fact, it follows none of the other universality classes. The critical scaling is completely off as you go to this 2D limit and this low temperature transition which we find in CGT. So what is happening inside the system? The magnetization, if you fit as a function of temperature, as I told you, is that if the magnons are gapless, if you have no anisotropy in the system, and it is gapped if you have anisotropy, so the dispersion relation, instead of going as just proportional to Q square, you will have a delta, and you can do a magnetization, the saturation magnetization, which we measured from the critical scaling analysis. If you fit it as a function of temperature, you can do this fit, and you can find out the value of the anisotropy gap inside the system, the gap which is present inside the system. And for a bulk, we find that the anisotropy is around 1.38 milli electron volt. But when you go to the very low thickness sample, the anisotropy has dropped significantly. At this low temperatures, the transition which is happening around 14 Kelvin, the anisotropy out there has changed. It has gone down to 0.1. This is, I'll come to that. So this is where we find that there is a significant change in anisotropy of the system as you lower the dimensionality of the system. And this is where we started talking to Prashanjit and his student. And what they did was, they did DFT calculations on this system. And so they did a DFT calculation for the bulk, for the bilayer, and for the monolayer case. And what they found is that if you look at the equilibrated structures by relaxing the structures down, for each of these systems, what they found is that as you go to lower dimensions, there is slight structural distortions which are occurring in the system. There is the chromium-chromium distance changes very slightly, the chromium-tellurium-chromium angle, that's very important, that changes, and the tellurium-tellurium distance also shifts. So there is slight sort of distortions which occur inside the lattice as you go down in dimension. And if you actually measure the magnetocrystalline anisotropy, so this is the density of states across the Fermi energy, and the tellurium is the one which actually gives rise to the spin orbit coupling. As you go from the bulk to the monolayer, you find that the contribution of tellurium to at the Fermi energy, that decreases significantly. So the spin orbit coupling is actually going down in the system as you lower the dimensionality of the system. And furthermore, what we did was we also calculated the dipolar anisotropy, which is the anisotropy associated with your dipoles inside the system. This is the electromagnetic dipole energy, the interaction between two dipoles. And we calculated the difference in dipolar energy if the dipoles are along the c-axis or they are in plane. And what you find is that the dipole anisotropy actually changes sign as you go from the bulk to bilayer, which means that there is a strong dipole, there is a strong demag factor, there is a shape anisotropy effect which is coming into the picture, which is actually competing with the magnetocrystalline anisotropy energy, and the total effective anisotropy actually in the system is going down. The exchange anisotropy they didn't calculate, but there are some work which actually there is a work which has actually looked at because of hopping and the chromium, tellurium, chromium, because of hopping along that also changes the anisotropy, and that happens because of the change in the bond angle. Because of this distortion as you go down to 2D layer, this plays a role, and instead of z-axis, it also starts bringing it down into the AB plane. So all these effects start coming into the picture, and we believe that there is a significant change in anisotropy which happens inside the system, and that is why we found that there is a drop in anisotropy as you go from the bulk to the monolayer case, because once you cleave the system, there are slight distortions which set into the system, and these distortions are driving the change in anisotropy, and these changes in anisotropy are very significant. We also did Raman scattering inside the system, in these systems, we did Raman scattering as a function of temperature. For different temperatures, you can see the breathing and the shearing modes, and these have a shift with temperature which is expected. There is an enharmonic fitting which you can do to actually explain the shift in temperatures. So that enharmonic fitting works up to a certain temperature, but then the shift in the Raman peaks, both the Raman peaks, is actually much more than what can be explained by the harmonic fitting, and that actually comes from spin-phonon coupling inside the system. So it's very sensitive to the phonon, and the lattice is very strongly coupled. Any sort of distortion inside the system is actually going to play up and change the anisotropy inside the system. So the basic idea that we had is that, of course, in the bulk system, it's all out of plane anisotropy. It dominates over any in-plane anisotropy component which is present inside the system. But as you lower the dimensionality of the system, then what happens is that this, there is a anisotropy exchange along the z-axis, and there is some anisotropy which is also present along the AB direction, and this starts competing along as opposed to along the Z direction, and it releases fluctuations, critical fluctuations in the AB plane, and you start seeing this new transition temperature which is associated with 14 Kelvin when this new anisotropy comes into the picture. So as you change the dimensionality of the system, we also believe, apart from the changes in anisotropy, the domain structure of the system is also going to change at lower dimensions. And this is sort of, people have looked at competition between short range and long range interactions. They have modeled these systems with short range and long range interaction, nearest neighbor, and interactions across the lattice. Not exactly our system, but these are slightly different systems, and they have looked at a combination between short range and long range interactions inside the system, and they found complete differences in the critical scaling and also the correlation lengths, whereas large correlation lengths develop as you approach the critical transition in the short range interaction models. In the mixed models, actually there is no divergence in the correlation lengths, because the correlation lengths in long scale interaction doesn't really make much sense, but there is still a divergence in the susceptibility which is seen, which is also something that we see. So clearly there is changes in the structure of the system, and so as you go from short range interaction, so in the bulk 3D case you have short range interactions inside the system, but as you go to lower dimensionalities, not only do you have the short range interactions, but you also have changes in anisotropy and long range interactions which are coming into the picture, and those are the things. So there is a crossover in criticality in the critical scaling exponents as you go from a short range interaction dominated to a much more complicated regime which actually develops at lower dimensions. Do I have 2 minutes? Yeah.
30 seconds more.
Sorry?
2 minutes and 30 seconds.
No. Okay. So, so this is where sort of we thought that this is something which is ongoing, so I'll not show much on this, but we do essentially something called magneto-optical imaging, where we actually send in a linearly polarized light, and then it is reflected and Faraday rotated, and we detect with very high sensitivity this rotation so that we can see local domain structures, and we can do interesting stuff with it. Namely, what we are currently doing is we are sending in currents through systems. It could be topological insulator, it could be a metal insulator transition superconductor, even these sort of devices, these sort of structures. We have not yet succeeded in putting current into these 2D layers, but that's something which we are currently attempting. But what you can do is with this is that you can see the self field which is generated by the current, and you can see where the current is flowing, and you can see if you can drive domains and so on inside the system. This is just an advertisement that you have. This is a Bi2Se3 crystal, and you can see the edge currents. This is actually the self field, the field distribution that you can see in this technique. You can see the bright and dark regions, which are the magnetic fields coming out of the plane and going into the plane because of a current which is coming in from the gold pads and going out of the gold pads. And you can actually see the edge currents. This is an inversion. You numerically invert this field distribution image and you can get the current distribution. You will see edge currents on the edges of these topological insulators, role of defects and so on. Metal insulator transitions, you can identify insulating phases and metallic phases. So this is where we are sort of interested to look at some of these 2D systems. But currently, what we are just attempting to do is that we have these layers of 2D materials which are on HBN, and we are trying to figure out or trying to see them what is the nature of the domain structure, because ultimately we map the local field distribution. And as you cool the system from high temperature to low temperature, the movie is not working here, but I would have liked to show the movie, but you can suddenly see these domains pop up. So this is one piece of CGT, and you can see that this piece of CGT is almost monodomain, and this edge is bright and this edge is dark. So it has a magnetization which is in plane, and the demagnetizing fields are pointing out of the plane, which is bright, and this is the dark region where they are going in. So we can see actually a domain structure, and then as you go to lower temperature, suddenly they disappear. And that is because we are actually, I think, the domains are suddenly shrinking and they are becoming much more smaller as we go to much lower temperatures. And that's where it is falling below our spatial resolution of imaging. We are trying to improve it. When we send in current, we'll see much more details, but that is all of the work which is going on. So let me summarize is that we found, before we actually could go to device structures, we found something very interesting, that when you go from the bulk layer to the 2D layer, there is new physics which emerges, and as you lower the dimensionality, you actually see changes in anisotropy. The critical universality class can completely change, and at these lower dimensions, there are unusual effects which you must take into account to actually understand some of this physics that is emerging, or which is emergent inside these 2D systems with lowering dimensionality. So with that, thank you.
Questions? Okay, I'll come there.
Hi, very nice talk. So, do you exfoliate these materials inside a glove box?
Yes.
And
but we have to take it out. But if you don't do it within 15 to 20 minutes, there is oxidation of the surface. Even your Raman signatures and so on can go off. So you have to prevent that. So you have to do it very quickly.
okay. And how does the magnetization change if you change the direction of the magnetic field?
So, okay, so in the bulk crystal, it's C-axis oriented, that's the easy axis, and AB plane is the hard axis. So the saturation fields are different. Now in the 2D case, I didn't show it, but we are not able to measure it in the parallel direction. We are only able to measure in this direction because we are getting the effective sample much larger. Once you put it like this, we just cannot get enough signal to actually see it in the other direction. So whatever analysis I showed you is essentially for field perpendicular to AB plane.
Thank you.
So, a nice talk. When you thin down your sample, you see towards low temperature 14K, or there is a downfall in magnetization.
There is a turnaround in magnetization.
But is that some kind of, not a ferromagnetic ordering, some other ordering?
I think it is still ferromagnetic. The thing is that you are measuring along the C direction. So the anisotropy, if it is shifting from the C and going into the AB plane, the magnetization which you are measuring along the C axis actually changes. So that is the drop that we are seeing. As far as till now, we have not seen any possibility of antiferromagnetic correlations which are developing around the 14 Kelvin transition. So it's just that there is a strong loss in anisotropy, and the system, because of developing shape anisotropy, pushes the magnetization in plane, and that's where you see that the magnetization starts turning around.
Okay, so is that a crossover or a phase transition?
It's a critical crossover because you go from one universality class which is sitting at 67 Kelvin to one which is at 14 Kelvin, which is a completely different universality class.
Thank you.
Very nice result. So first thing is that your transport data, I saw that.
No, we have not measured transport on this as yet.
But the data shows it's a very weakly coupled. Near the transition, you have very little effect.
Yes.
Right?
No, which?
In CGT.
Yes.
you see semiconductor-like behavior, but
Yeah.
near the ferromagnetic transition, it seems that
It is a semiconductor.
no, it's a semiconductor, but ferromagnetic transition, you have very little kink, right? I'm saying in the transport. My question is that through transport, can you detect the ferromagnetic transition?
In transport, it's in bulk you have the semiconducting behavior at 67 Kelvin. But in the 2D case we have not yet
Not
measured
2D,
transfer.
even in the bulk.
Yeah, it's a
Because in
proper semiconductor.
FGT system we see transport is coupled with the magnetism very
FGT
much.
is a different system.
Yeah,
It is a completely different system.
Yeah.
It is 3D Heisenberg scale, the universality class which comes in FGT. In CGT, you see the semiconducting behavior in bulk. In 2D, we have not yet measured. That's where we are actually doing experiments to do the cell field imaging and transport simultaneously, so that we can see where the current is flowing as well as evaluate the transport signatures inside the system. And if there is disordered structures, then you will have scattering and so on. So
second thing is that could you do Raman below 20 Kelvin to see the
no,
structure?
unfortunately, we couldn't go below 20 Kelvin.
Okay.
Our system is not, doesn't allow for that.
Okay, thanks.
Yeah.
I just wanted to ask, how much is the substrate effect? Because you have put
In
this-
HBN, we found that there is very little substrate effect. But when we go to silicon substrate, there is chromium germanium telluride and there is chromium silicon telluride. There are these two systems, and we feel that in that case there is a strong, and that is why people had been missing the thing to actually see this. The substrate interaction with CGT can be pretty strong.
As you're thinning down the sample, the transition temperature should also decrease. Right?
We find that in this case, as I showed you, it's close to 67 Kelvin, it's 65 or so. But there is another transition which is at lower. Now, if you take the average of these two transitions, then certainly, so certain experiments do an average measurement which actually can show a lower transition. But there are two distinct transitions that are there inside the system.
Yeah, but that transition should also, drastically decrease from the bulk to.
No, in the bulk, there is no 14 Kelvin transition.
That 60 Kelvin, around that 60 Kelvin.
67 Kelvin is where it is, and we find it is maybe 64 or 65 in the thinner samples of 2D case. But there is another transition which is sitting at 14 Kelvin.
Okay, so basically we are taking the average of.
We are not taking the average. If you do, then you would think that there is a lowering of transition temperature.
Okay, thank you.
But at least as far as we are concerned, we see two distinct transitions.
Any other question?